Last time, I derived unit stream power, which is omega here on your screen, based on arguments starting with the loss of potential energy with distance downstream, the conversion of that potential energy into a combination of heat from dissipation against the bed and banks and turbulence inside the flow, and kinetic energy. So long as the flow is uniform, the water isn't accelerating, and the same amount of sediment should be moved into and out of each cross-section of the flow. And therefore, any expenditure of kinetic energy, or of potential energy into kinetic energy, rather, should relate to the erosion of bedrock, which is causing formerly inert mass, so formerly stationary mass, to become detached and then to start moving downstream. And that will eventually relate to erosion, right? And give us some relationship for bedrock erosion. And you can also imagine that, I say heat, but just in general, mechanical energy, that some of that energy in the flow is going to breaking up that bedrock, and some of it is going to actually causing the erosion and transporting it. And so if the bedrock is more competent, so less easily broken down, it just takes a lot longer to expend enough energy to get ready to remove a chunk of the bed and send it downstream. But this whole time we've been talking about energy, and prior to this, I was discussing shear stress as this key parameter that we could calculate from equations of fluid flow to relate to sediment transport and bedrock erosion. And so what I want to show you right now is that there is a way of relating unit stream power to shear stress that shows the very, very tight relationship between these two. So this is going to be the question for today, which is, what about shear stress? And so I'm going to start out with this equation that we have right up above for unit stream power. I'm going to rewrite it, and everything here is going to be green just so you can see when I post this PDF that this is all one big aside, and we can get back to talking about stream power if you want. But this, I think, for those of us who like to have a self-consistent way of thinking about these problems, I want to present this just because I feel like this is really helpful, at least to me, in linking these concepts together. So this little omega, which is unit stream power, is equal to rho g times q, discharge over channel width, times slope. And remember last time we actually packed a bunch of terms into Q, and I'm going to unpack them again. So just say Q is equal to, and I had this delta y, delta z, u bar, and delta y, it turns out we ended up through the rectangular channel assumption, saying that delta y, which would be, maybe I'll make that a little clearer, this thing right here. Delta z is this height right here. So delta y is going to be equal to the width, and delta z is going to be equal to the height of the channel, the height of the flow in the channel. And so u bar, of course, is just the mean velocity, so that stays the same. So let's carry on with that unpacking. So omega is equal to rho g b, or I guess HBU, slope, divided by width. And so these two width terms will cancel out. And now check it out. We have rho GH, this U sitting there, and then the slope. So this is equal to rho GHS, velocity. And we know from the depth slope product that for a steady uniform flow, this is equal to the bed shear stress. So therefore, we can say that omega is equal to tau b times velocity. So there's this direct relationship between those two terms. And if we want to suss out a bit more about the nature of this relationship and how to more directly link the shear stress to the stream power, we can go back to one of the formulas we discussed for flow velocity, which is the Darcy-Weisbach formula. And in that, we have a relationship for shear stress that says that tau b is equal to rho CF, so this is a friction factor, times mean velocity squared. And if you want to just understand a bit more about where this comes from, you can also remember that this is equal to rho density times u tau, so this is the shear velocity, squared. And so you can think of this friction factor as something that is converting between the mean flow velocity and the velocity that tells us something about the intensity of the turbulence, which then leads to, dissipation of energy against the beds and banks. All right, great. So that's Darcy-Weisbach formula. Well, what we can see then is that there's a way of then converting between velocities and stresses. And so let's flip this thing around so we can actually solve for u bar. So we have u bar is equal to, and then we have tau b on the other side of the equation, over rho CF. And I've left a little bit of space because remember we had u bar squared. And I'm going to take the square root of everything. And, like if we were being really formal about the mathematics, we'd say, plus or minus the square root. But this is physics. This isn't math. We know that these values are positive. There's a positive shear stress. Mass, the density is real. The friction factor is real. We could have a directional shear stress if that were going, upstream. But we're just going to consider everything as positive scalars. And so we'll just keep this positive and keep it simple. So therefore, if we take this then back to little omega, which is unit stream power per unit width, then we have that is equal to tau b times u bar. And if we plug in that u bar, what we then get is that this is equal to tau b to the 3/2 power over square root of rho times the friction factor. And then just to remind you what that is in the end, that this is equal to rho g q over b times slope. And so therefore what we can see is that the stream power scales with the basal shear stress to the 3/2 power. So nice and simple, and we can see therefore that in the same way that we can think about power and energy dissipation, we can also think about these shear stresses, and that both of them essentially can be thought of as these terms that are driving erosion and driving transport of material.